All right, welcome to day 5 of remote learning. Today's task is to work on solving trig equation worksheet number 2. I wanted to help you out with a few examples to get things started. Also, I've got Owen and my dog Mason with me here. As you can see, they are both really enjoying their remote learning experience. Dog's had enough. Okay, so a couple examples for today. First one, we're going to solve on the interval 0 to 2 pi. And the example is 2 sine squared plus 3 sine theta equals 2. Okay, so solving 2 sine squared plus 3 sine theta equals 2. Let me just bring that a little bit closer so you can see a little better. There you go. All right, so if you remember back to our unit on logs and exponentials, we saw quadratic forms quite a bit, and we'd take a problem like this, and maybe we would rewrite it like 2 happy face squared plus 3 happy face plus equals 2, or minus 2 equals 0, even better. So we get all the terms on the same side of the equation, and it's all set up for factoring. And when we factor that, of course, we would get 2 of these minus 1, and then happy face plus 2 equals 0 to show the 2 linear factors, just like that. And of course, substituting sine theta back in for the happy face would give us the expression 2 sine theta minus 1 times sine theta plus 2 equals 0. Okay, the one thing to keep in mind, since these are trig equations instead of just regular old quadratic equations, with a quadratic you'd be expecting 2 solutions, not necessarily 2 real solutions, but it should have 2 solutions over complex numbers. With trig equations, that's not necessarily true. We do get 2 linear factors, right? But you'll note that the first linear factor, when we set that equal to 0, that will lead to the equation sine theta equals 1/2, which will have 2 solutions of its own on the interval from 0 to 2 pi, a solution on the way up, a solution on the way down. Meanwhile, the second linear factor will lead to the equation sine theta equals -2, and we know -2 is not a value that sine theta ever achieves, so that will lead to no solutions on the interval from 0 to 2 pi. So that's how these are a little different maybe than your standard quadratics. So to finish up the problem, I need to know where is sine theta equal to 1/2, and if I can get that answer, then I've got the answers to my original problem. So maybe I'll draw a little unit circle here, and then a horizontal line at y equals 1/2. And I can see my 2 solutions are pi over 6 and 5 pi over 6. And that's it. So I write those like this. Theta equals pi over 6 and 5 pi over 6, and we're done. Okay, second linear factor didn't lead to any solutions because sine was never equal to -2. So there's that. Okay, let's look at the second example. The second example doesn't look like a quadratic, but it's an important one to consider. Example 2 is 2 sine theta times cosine theta equals sine theta. So this is second degree because I have a sine multiplied by a cosine. A tempting thing to do to start this problem would be dividing both sides by sine theta. If you did that, this is what it would look like. 2 cosine theta equals 1. So that's dividing both sides of the equation by a sine theta. It certainly simplifies things, but here's why that's a bad idea. That's a bad idea because sine theta, as we know, is 0 quite often. That means there's a lot of solutions that would be losing if we divide both sides by sine theta. We don't want to lose those solutions, so a better idea would be to treat it like a quadratic and group everything on the same side of the equation. So 2 sine cosine minus sine equals 0, and try to factor. Okay, this would be factored with the GCF technique where there's a sine theta in both terms. I can factor it out. That'll give me sine theta multiplied by 2 cosine theta minus 1 equals 0. And now we can see both linear solutions. Sine theta could be equal to 0 to make this equation true, or cosine theta could be equal to a half to make that equation true. So I'll consider both of those. Either sine theta is 0 or cos is positive 1/2. On my unit circle, which I like to use as a guide, I'm thinking about drawing a horizontal line at y equals 0. That shows me two solutions. Note that those would be the two solutions that you would have lost if you divided both sides by sine. And then x equals a half is a horizontal line at x equals a half. Show the other two solutions. And now I can see that the four answers to this problem on the interval 0 to 2 pi are 0, pi over 3, pi, and 5 pi over 3. Okay, so I'll write those down, and that will conclude example 2, 0, pi over 3, pi, and 5 pi over 3. Oh, one thing I should say, it's a good habit to get into to start checking your solutions, plugging them back into the original to show that it works. They all will work in this particular example. There's going to be some cases very soon where we come across extraneous solutions, and that's a good habit to get into so you don't fall victim of stating extraneous solutions as solutions to the problem. So just as an example, for pi, when I plug pi back in, 2 times sine of pi times cosine of pi is 2 times 0 times negative 1, which is 0. And on the other side, sine of pi is 0. So that shows that pi works. You could check with the other ones. They will all work, but in the future that won't always be the case. You'll see that in Solving Equations Worksheet 3. Okay, example 3. One more problem to look at. Let's say we have the equation that we want to solve on the interval 0 to 2 pi, and it is tan squared theta minus 4 tan theta plus 3 equals 0. Okay, so if I try that substitution again, I see a quadratic form like this, which is easy enough to factor, but just suppose for a second that you don't see how to factor that particular equation, or you don't feel like fiddling around to figure out how to factor it. I want to point out that the quadratic formula will work for equations that don't factor. So my variable here is the happy face, which of course is tan theta. So I'd say tan theta is equal to negative b plus or minus square root of b squared all over 4ac. So that'd be the opposite of negative 4, which is positive 4, plus or minus the square root of b squared minus 4ac is going to be 16 minus 12, so it'll give you another 4 all over 2a, which is over 2. That leads me to the two solutions for tan theta. Tan theta is 4 plus root 4 over 2, which is just a 3, or tan theta is 4 minus root 4 over 2, which is just tan theta equals 1. Great. And notice that those would be the two linear solutions that you would have gotten if you just factored it, tan theta minus 3, tan theta minus 1 in the beginning. So for problems that don't factor, or ones you don't want to fiddle around with factoring, you can always use the quadratic formula to isolate the variable. Okay, so now what? Tan theta equals 3, tan theta equals 1. Oh, I know tan theta equals 1 at pi over 4 and 5 pi over 4. You can see that from your unit circle, right? Pi over 4 and 5 pi over 4 would be two solutions to this problem. But what about tan theta equals 3? You need a calculator for that one. And at the moment, my daughter's using my calculator for her Common Core packet. But I believe tan inverse of 3 is about 1.25. So that would give us our other solution. Keep in mind that if you're using the calculator, it's only giving you one solution because it's an inverse, so you have to add the period to get the other. So in all, all of my solutions would look like pi over 4, 1.25, pi over 4 plus pi, which is 5 pi over 4, and 1.25 plus pi, which 1.25 plus 3.14 will be about 4.39. And there's the 4 solutions to example 3. If you plug them in, they'll check out. Of course, these are approximate, so you'll get approximately 0. Let me know if you have any other questions on solving trig equation worksheet number 2 on the discussion board, and I can answer those.